Our parameter mu represents the mean value for a population for some parameter that we're measuring. However, because it applies to the population, we can never know exactly what it is because it would require testing all members of that population. Therefore, we take a sample and we can calculate the mean of that sample, and we want to use that information to help us figure out what the value of mu is. But we don't expect the value that we get for x bar, our sample mean, to be exactly our population mean. Depending on the sample we get, we may have samples that are a little bit below our population mean, a little bit above. And so we know that the population mean is going to fall somewhere near our sample mean, but not exactly there. So what we would like is an idea of where that mean falls. And to do that, we calculate a confidence limit where we have a lower and upper limit on that interval to show us where we think that the value of our population mean will fall, since we can't know exactly what it's going to be. So this represents a confidence interval where we have a certain degree of confidence that our parameter mu will fall. And the percent of confidence we have is expressed in terms of 1 minus alpha, and we'll use that alpha later, but we maybe have a confidence interval, 95% confidence interval, that tells us where we think mu will fall, and in that case that would represent an alpha of 0.05, okay, because our confidence is 1 minus whatever alpha is. Now this relates to probability, and we'll take a look at our probability in terms of our sample mean. We take a sample mean. We expect it to fall between two limits with the probability of 1 minus alpha. And looking at doing again our transformation to a standard normal random variable, we find the probability that it falls between two limits. And sigma divided by the square root of n, since it's the sample mean, not just x but x bar. Doing our transformation, we can replace these values of x1 and x2 with values of minus z. We designate this as alpha over 2, and positive z of alpha over 2. And so we've got the same value at either side of our inequality, but the positive and negative versions of them. And if we look at where these numbers come from, the z of alpha and the z of alpha over 2, we can see that in our normal distribution that they are at either side of the either tail of the distribution. This is z of alpha over 2. This is minus z of alpha over 2. And what that designation represents is that the area above this limit, the area, and therefore the probability, is at either side alpha over 2. And so that means because the entire area under the curve is 1, I take the entire area of 1, subtract alpha over 2 times 2, gives me an area of 1 minus alpha between those limits, which is the probability that we were looking for here. So those values of z above and below our mean, above and below, can be used in our confidence interval calculation. So if I take the lower limit and the upper limit, and now solve for mu, because I want a range that gives me lower and upper limits on mu. This probability is 1 minus alpha. I take the sigma over the square root of n and multiply it times both sides of the inequality, minus z of alpha over 2 times sigma over n, and then at this side I'll have z of alpha over 2 times sigma over the square root of n. And so that takes this part out of the denominator and takes it to either side. And then if I want mu by itself, I subtract x bar from this side and subtract x bar from this side. So that leaves me with a negative mu inside my inequality. If I want to change that to positive mu, take the negative sign off, I multiply through all three parts by minus 1. Multiplying an inequality by a negative sign turns the inequality signs around. So if I multiply by negative 1, it becomes positive, 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 and this term, this z of alpha over 2, becomes negative. So to slightly rearrange things here, get x bar plus z of alpha over 2 times sigma over the square root of n is greater than mu, which is greater than, again, the greater than because we multiply by a negative number, and here we have minus z of alpha over 2 from sigma over the square root of n. And so this is my lower limit, because my signs have turned around. My lower limit is now on the right side, my upper limit is on the left side, and I can generalize this as my limits on mu, the upper and lower confidence limits, are x bar plus and minus a value of z, where z comes from the distribution depending on what level of confidence I want to have. The higher this area becomes, which means the more confidence I have, the bigger my value of z is going to be, because I have to move further and further out to get that area in the middle here. And then I multiply by sigma over the square root of n. So as the standard deviation, as sigma gets bigger, so as I have more variability, that means the size of the interval, the above and below x bar, the size of the interval will also get bigger. So if I have a random variable that has a small amount of variation, a small standard deviation, then I'll have a relatively small confidence interval. If I have a random variable that has a lot of variation, so a high standard deviation, that means I'm going to have a very wide interval, because this will be a very large value.